Welcome to the next video in the systems programming video series. To discuss what we're up to in this video, let's keep in mind that we just finished. What did we just finish? We just finished reading this section of the text. We've already done that assignment much earlier. And it also wants us to read chapter 10. So we finished, these sections, recommended for chapter 7. Chapter 10 is a summary of kind of everything that we've seen so far. So I don't think that's really worth the time spent. I think the chapter is very self-explanatory. So I don't think much is gained by me talking through chapter 10. So instead, we'll come down to the next assignment, and that is here. And there's a study guide. We could talk about that, but I kind of want to maybe just skip to the jam. Those are usually more programmy and interactive, or something like that. And in any case, I'd just maybe do this, not worry about the study guide, and then we'll move on to, I think, in fact, we would still be ready to move on to the next programming assignment. So what I'm going to do starting now is this jam, and then after that, we'll do the next programming assignment, and then we'll return to the reading. So in any case, that's what we're up to. So here in the jam, we are going to look at unsigned 4-bit integers written in decimal and indicate whether there is an overflow and what the result is. So express your final answer in hex and show your work. Okay, so for this question 1, and I guess, what do we want to call this? Can I just say 5 shift 3, and what, we're going to compute that. So this is a bit shift. We want to understand the bits. So 5, what is 5? Well, 100, that's 4, so 101, that's got to be 5. And if we shift that by 3, now, and I guess I should pad this so that we understand that it is 4 bits. And keeping in mind this is an unsigned bit, I mean 5 would look exactly the same even if it were signed, but no matter which signing system we used or whatever. It's important to represent 5 in its bits because we're going to bit shift it. It's not so important to represent 3 in its bits because we just want to bit shift this 3 times. So there we just want to use our understanding of what 3 is to perform this. So if we bit shift this 3 times, then effectively what we should get is that this 1 will shift 3 places left. Everything else goes away, right? Basically due to overflow. If when we take this first 0 and bit shift it once, then you wouldn't really think of that as an overflow. So that's like no overflow. But then this 1 moves over to that position and we bit shift again, and that's going to cause an overflow because a 1 is, in a sense, leaving the binary number. So I would say that's an overflow. So there is an overflow, and the result of bit shifting should be this right here. When we left shift, both in the arithmetic as well as in the logical bit shifting, a left shift simply places zeros to the right of all of the shifted bits. So that should be the result. Now, if we want to test this out, it even says that, you can test these things, right? Compute the following results for it and to show your work. So what I've done is I've come over to the jam JO3 thing that was distributed. Now, just for the sake of not having to make a whole new file and compile it and whatever, I'm just going to use this scramble.c, right? It's here for the last question, but I'm just going to use it anyway to do some quick printing for the first part. Now, there's going to be a caveat when we try these things out in C because, it only lets you store a byte, right? The smallest thing you can store is a char, and a char is a byte, which is 8 bits, which is twice as much as these 4-bit integers that we're talking about here. So what we'll have to keep in mind is that when we print this thing in hex, we're only going to it's going to give us 2 hexes, right? Each hex is 4 bits. So to get all 8 bits, then it's going to give us two hexes for any char. By the way, I'll just go ahead and say that I'm going to like declare a char x equals 5. Um, and maybe just to make sure that it understands what I mean by that, I'll say unsigned char, although I think the default on my system is that chars are always assumed to be unsigned unless otherwise specified. But anyway, let's just go with that. So unsigned char is equal to 5. Note, not with the quote marks or whatever to make it like the character 5. It's really understand, just because chars are understood as basically just bits, then when I say that it's equal to 5, it's just going to store the binary representation of the number 5 in the unsigned number system. So don't be deceived by the fact that it's declared as char. It really understands it as a number. So anyway, and then what I want to do is I want to print the result of bit shifting. So let's go ahead and say printf, and I'd even like to print it, let's say, in hex. That's already, that's kind of nice just to see it that way. It'll take a little bit of interpretation, but I mean, I guess that's actually how we want to enter the answer anyway. So, oh, and I guess, should I, oh, yeah. And sorry, before getting to that, I should actually just go ahead and show you what this binary number is when written in hex, because that is, after all, how we're supposed to write our answers. Well, this is effectively the number 8, and 8 in hex is just 8. So let's just write OX8 to indicate that that is the hex digit 8. Okay, so that's what I predict, right? So what it's going to do is it's going to bit shift 3 times because it's a byte when we test this out, then there's not going to be an overflow. This one is actually just going to move into the next byte to the left, and it's going to do so in 2 places, right? It's going to it's going to move once, just within this 4 bits. It's going to move a second time because we're shifting 3 times. So it's going to move a second time, putting it into the units digit of the next hex. Okay, then it's going to shift one more time and put it into the, so to speak, the twos place for the hex. So anyway, my calculation is that basically when we actually run this in code, the first hex is going to be 2 because this 1 shifts into the 2 place, and then it's also going to have a 0 in the, so to speak, ones place. So in any case, I predict that the leftmost hex is going to contain the digit 2, but we want to ignore that anyway. I just want to say that prediction so that I demonstrate to myself that I'm thinking about this correctly. And so I think the left digit digit in hex is going to be a 2, and the right digit, the one that we actually care about, is going to be an 8. So let's run it and check that I'm right. And so I'll just say x shifted by 3, and that should be enough to see the result. So if I go ahead and say make scramble, and it makes, and if I run scramble, 2.8, exactly as predicted. So very good. So the answer that I gave here is correct. Let's move on and do the next thing is to talk about one. Oh, I'm sorry. I am, because just in logic we use a wedge symbol to represent and so my mind went straight to reading that as a bitwise and, but of course, right, when we're in C, the much more natural symbol to use for bitwise and is the ampersand. And so yes, I was forgetting that the caret symbol in C is the bitwise XOR operation. So I should, yeah, let's come back over and recompute this. So this is supposed to XOR. So let's say 0 XOR 0 is 0. 0 XOR 1 is 1. 0 XOR 0 is 0. 1 XOR 1 is 0. So there's performing the XOR. And then if we write this in hex, that should be 4, right? So this is just in the 4's place. So, okay, and then that makes total sense of what we see in the print for the program. Okay, so there we have it. We have now computed 1 XOR 5. Okay, bitwise XOR 5. Now we're going to compute. Oh, and by the way, I guess I should make explicit here that there was overflow. And here there was no overflow with these logical bitwise operations. There's never overflow because they are just, like things don't carry in any sense from one digit to the next in these logical operations. So now we're going to do 5 minus 6. Let's represent both bitwise. So that's going to be 0, 1, 0, 1 for 5 as we're used to. Minus 6 is one more, so that's going to be 0, 1, 1, 0. And so how do we compute this subtraction? So we're going to use that whole trick of bit flip add 1. That even works when we're doing unsigned integers. So, and I think actually let's talk about what we expect the result to be before we actually compute it according to the rules. Now, of course, if this were any other class, we'd say that that's -1. But these are unsigned integers, and so we can't have -1. So in the unsigned integers, the discontinuity happens at 0. And so when we go from 0 to the left by 1, then this like wraps back around, so to speak, to the largest positive number that can be represented by the system. And so if we're dealing in 4 bits, then the largest possible number you could represent is 15, sequence of all ones. And so that's what we should expect this to come out to. This should evaluate to bit in binary a sequence of all ones, which is the number 15. But let's see how that comes out when we simply perform the arithmetic steps. So we are going to bit flip the second number. So this is going to be 0, 1, 0, 1 plus. Now here, if we bit flip, we get 1, 0, 0, 1, and we're going to add 1. So this is like the recipe for how you subtract numbers. Let's go ahead and further simplify this. So what is this going to be? I'm going to write the rightmost digit first, just because that's the way that we compute this. So the rightmost digit, I'm just going to do it all at once, is a 1 and a 1 and a 1. So that's going to cause the rightmost bit to be a 1 with a carry. So then in the next place, it's 0, 0, 1, so 1. No more carry, so now it's going to be 1, 0, so that's a 1. And then in the leftmost place, a 1. Exactly as predicted, and in hex, 15. What is 15 in hex? That's F. So that's the hex result. Was there an overflow? I think the rule that we said for overflow when it comes to unsigned integers, and I think like we know that we should say that there was an overflow because we crossed the discontinuity. But let's give the technical reason, like the one in terms of like carries and whatnot, for like carry in and carry out of this and that digit. So what was the rule for unsigned integers? This was the one where we consider the entire operation as a whole. Now, because it is a subtraction, then basically the carry in to the entire system, which is to say to the least significant bit, was this +1, right? Like you can think of this +1 as just doing a +1, but when talking about carries, we really tend to think of that as like an initial carry in of 1. And then the question is, was there any carry out? And we recall that in this final bit, what did we carry out? It was a 0. So the carry in to the whole thing was 1. The carry out to the whole thing was 0. Since those are mismatched, the rule was that there was an overflow. Okay, so that problem is now done. And I guess now we are moving on to the signed integers. So let's talk about the signed integers. And so we're going to compute 7 shifted right by 1. Now, since these are signed integers, then I think it makes the most sense, right? We're going to use 2's complement. And so if we're doing signed integers, then we should, right, like the natural thing to use for a right shift is so what we use for this when working with signed integers is the arithmetic shift. and that preserves the leftmost bit. So we want to go ahead and write the number 7, which would be in signed integers, what we could say is, because we want it to be positive, so that's 0, and then put that's a 4 and a 6, right? Like, because if you think of that as like the fours place, then we put we have a 4, we have another 2, and another 1. So there is the number 7, and we're going to right shift it by 1. And we are going to basically preserve the leftmost bit. So then this results in 0, 0, right? Because we're basically making a copy of that leftmost 0. And then writing 1, 1, and this is the hex number of 2 plus 1 is 3. So there is the shift, and the rightmost bit uh, basically had like a carry out of 1, so I would say that there was an overflow. So was overflow. Okay. So next we are going to bitwise OR the numbers 1 and -5. So first thing we want to do is figure out how to write those numbers. So okay, so we're going to do 1 or -5. We'll write these as their binary numbers in the signed integer system. So that's going to be 0, 0, 0, 1. That's +1, and we are going to bitwise OR that with -5. So if it's, let's just say like, how do I want, let's maybe do it like this. Like, I don't have some kind of like planned system for how to write these stages of computation out, but let's just write down +5, which is 0, 1, 0, 1 with a negative sign on it. So indicating that that's still something to compute. Now, how do you negate a number? You bit flip and add 1. So let's write that now. So we're going to go 1, 0, 1, 0, but then add 1. So carrying on the computation, we get zeros like that, bitwise OR with the number 1, 0, 1, 1. Okay. Now that they are in binary, we can bitwise OR. So we get, and I have not been checking my answers. I guess I probably should. Yeah, I did it. Okay, so I only missed one. So let's go back and make sure that if we look at the unsigned char of 5 and 6, so let's say 5 here, 6 here, and I want to do 5 minus 6. So let's look at the thing that produces, all F's. So that makes some amount of sense. I mean, the most important thing is that the rightmost thing is an F, which is a sequence of all ones, which is the same answer as what we got. I guess maybe this is something to be careful about, that like when we performed this subtraction, I think maybe it decided that subtraction is just something it doesn't want to do with charts, right? Basically, what I'm worried about is like how many hex characters there are. There's way more. Like, there should just be 2 if it were taking everything to be a char. And I think the fact that there are this many means that it sort of turned everything into an int in order to perform this operation. So anyway, I think I am confirmed. It's just worth being careful and realizing that when you perform this subtraction operation, I guess the compiler doesn't want to do that with an unsigned char. So it turned everything into an int, and that's why we get this extra quantity of bytes. So anyway, okay, but I think we are confirmed in our answer here. So let's now turn these into signed char values. And I want to compute 7 bit shifted by 1. So I'm going to say 7 here, and I'm just going to bit shift 7 by 1. Let's make sure that we get the result that I believe we should get. Oops. Oh, and it doesn't like that. Yeah, I don't like this warning system. I'm going to go to the make file and turn these warnings off. Try this again. Okay, I think that's fine. And it computes 3, and was 3 my answer? It was my answer, so very good. So I'm confirmed in that one as well. Okay, cool. And so anyway, let's get back to computing this. So this should be, this is a not an exclusive or, but a regular or, so this is going to be 1, 0, 1, 1. And now we want to write that in hex, which is going to be, so the leftmost one we regard as a 8 plus 2 plus 1, so 11. A is 10, B is 11, so there's the hex. Now let's confirm this. So what am I doing again? I'm doing 1 or negative 5. So for a signed char, 1 or negative 5. Then if I bitwise OR these values, then what does the computer say? Again, expecting at least one more hex than I want. It should be 0 in this case. Oh, interesting. So I got the value B, which I knew that I should. I wonder if just any negative on a char gets, right, kind of causes it to just change it over to an int and get all these extra bits. Well, I think all these Fs, right, that's just a sequence of all ones. And I think that makes sense because we're getting this negative value that, pads out all the left bits by ones and then causes all the hex codes to be Fs. So I think that makes sense. I wish we could compute these things more directly without seeing these unwanted bytes. But in any case, I think we are confirmed in our answer, so I'm not that worried. Okay. Okay, I think we're done with that one. So let's now talk about negative 2 plus 5. And let's just do out the working. So let's say that this is negative, the number 2 as we know it in binary, and then plus 5, so that would be that. And then we'll compute this by saying that we bit flip, so that's 1101, add 1, and then the other number stays as before. We will compute that, so that's 1110 plus 0101. We will sum these values. Okay, so let's work from the rightmost bit. So that's going to be a 1 in the rightmost, then 0 and 1, so that's a 1, then 1 and 1, 0, carry a 1, so 0, carry a 1. When you carry, nothing happens. Oh, and before actually doing this, what should we expect the result to be? Because here, I think here you couldn't really reasonably have any expectations. There's nothing that we naturally think should be the result of that. But here, because we're working with signed numbers and we're adding a negative and a positive, we should expect that there is no overflow. With 2's complement, the discontinuity does not happen at 0. And so we would just expect this to come out 3, with no overflow. Well, that's exactly what this is, right? So this is exactly the hex code for the number 3. So let's just confirm this in our demonstration. So what this was, negative 2, positive 3, no overflow. We're summing these numbers. And I think, right, we'll again get those padded out bytes filled with Fs again because of the presence of a negative number, but we won't see anything weird happening. If there was an overflow, we might see something weird happen, but in any case, we're not going to see that here. So the number, oh, right, I did not set this to 5, which is what the problem requires. So, okay, so we are confirmed in that solution. And okay, so this has been a bit of a long video already, so we'll just pick up question 2 about floating point numbers in the next.